Imagine standing on the surface of an alien world bathed in the crimson glow of a dim red sun, permanently fixed in the sky. This isn't science fiction. It's the reality that would greet any traveler who could reach Proxima Centauri B, the closest exoplanet to our solar system orbiting the nearest star beyond our sun. This discovery has ignited imaginations and scientific curiosity worldwide, offering humanity its first potential interstellar destination less than 5 light-years away. Proxima Centauri, the diminutive red dwarf star that serves as our stellar next-door neighbor, represents far more than just a cosmic proximity record. It's a gateway to understanding the most common type of star in our galaxy: small, cool, and long-lived red dwarfs that outnumber Sun-like stars by a significant margin. While invisible to the naked eye from most northern latitudes, this faint stellar neighbor becomes visible through telescopes with apertures exceeding 10 centimeters for observers south of 27 degrees north latitude. Its discovery as a stellar companion to the Alpha Centauri system in 1915 by Robert Innes marked the beginning of our scientific fascination with this cosmic neighbor. The official announcement of Proxima Centauri B in August 2016 by the European Southern Observatory sent shockwaves through the astronomical community. This groundbreaking discovery emerged from a meticulous 15-year analysis of observational data collected by a team led by Dr. Guillaume Anglada-Escude from Queen Mary University of London. The bulk of the critical observations occurred during the first half of 2016 using the High Accuracy Radial Velocity Planet Searcher, HARPS, instrument mounted on the 3.6-meter telescope at La Silla Observatory in Chile. This sophisticated spectrometer, capable of detecting velocity changes as small as 1 meter per second, was central to the Pale Red campaign, a name deliberately echoing Carl Sagan's famous Pale Blue description of Earth. The detection method relied on the radial velocity technique, which measures minute periodic shifts in a star's spectral lines caused by the gravitational tug of orbiting planets. For Proxima Centauri, these subtle Doppler shifts revealed the presence of an Earth mass companion completing an orbital dance every 11.2 days. With an orbital radius of approximately 7.5 million kilometers, 20 times closer than Earth's distance from the Sun, this exoplanet exists in a region where stellar proximity creates extreme conditions unlike anything in our solar system. Despite its remarkably close orbit, Proxima Centauri B resides within what astronomers call the habitable zone, the region around a star where liquid water could potentially exist on a planet's surface. This counterintuitive reality stems from Proxima Centauri's nature as a red dwarf, with a surface temperature of just 3,042 Kelvin compared to our Sun's 5,772 Kelvin. The star's modest output, merely 0.17% of the Sun's luminosity, with over 85% of its radiation in the infrared spectrum, results in an equilibrium temperature on the planet's day side of approximately 234 Kelvin. While this might seem frigid, it's warm enough that liquid water could potentially exist in the Terminator region, the perpetual twilight zone between the scorching day side and freezing night side. The challenges to habitability on Proxima Centauri B are formidable. The planet receives approximately 400 times more X-ray radiation than Earth does from the Sun. Red dwarfs, like Proxima Centauri, are notoriously active, prone to frequent and powerful stellar flares that can dramatically increase high-energy radiation output. During these events, the X-ray flux can surge to levels thousands of times greater than Earth experiences, potentially stripping away planetary atmospheres over time and breaking down complex organic molecules essential for life as we know it. Yet this very hostility makes Proxima Centauri B scientifically invaluable. Understanding how planetary atmospheres evolve under such extreme conditions informs our models of atmospheric retention and loss, critical knowledge for assessing the potential habitability of the thousands of red dwarf systems now known to exist in our galaxy. Recent observations by the James Webb Space Telescope have begun to probe the atmospheric properties of similar exoplanets, though Proxima Centauri B's proximity to its bright stellar host presents unique observational challenges. Proxima Centauri itself is a fascinating object of study. With a diameter 7 times smaller than the Sun and a mass approximately 8 times less, this M-dwarf star exemplifies the most common stellar type in the Milky Way. Its faintness, requiring telescopic observation despite its cosmic proximity, highlights why red dwarfs remained largely unstudied until relatively recently. The star's longevity is staggering. While our Sun will exhaust its hydrogen fuel in about 5 billion years, Proxima Centauri has sufficient fuel to shine for trillions of years, potentially providing stable conditions for life to emerge and evolve on orbiting worlds. The Proxima Centauri system exists within the broader Alpha Centauri triple star system. Proxima is gravitationally bound to the binary pair Alpha Centauri A and B, which orbit each other at distances ranging from 11 to 36 astronomical units. This distant companionship, approximately 15,000 astronomical units from the binary pair, creates a complex gravitational environment that may have influenced the formation and evolution of Proxima Centauri B. The system's total distance from Earth, precisely measured at 4.246 light-years, makes it not only our closest stellar neighbor, but also a prime target for future interstellar exploration concepts. The discovery of Proxima Centauri B has profound implications for our understanding of planetary formation. Finding an Earth-mass planet in the habitable zone of the nearest star suggests that such worlds may be extraordinarily common throughout our galaxy. Statistical analyses of exoplanet discoveries indicate that approximately 20 to 25% of Sun-like stars host Earth-sized planets in their habitable zones, but red dwarfs, being far more numerous, might increase this fraction significantly when their planetary systems are fully accounted for. Despite the excitement surrounding Proxima Centauri B, several mysteries remain unresolved. Does it possess a protective magnetic field to shield against stellar radiation? What is the composition of its atmosphere, if one exists? Could any form of life withstand the intense radiation environment? These questions drive ongoing observational campaigns and theoretical modeling efforts across the global astronomical community. The Breakthrough Starshot initiative, announced in 2016, aims to develop technology capable of sending gram-scale spacecraft to the Alpha Centauri system within our lifetimes. These nanocraft, propelled by powerful Earth-based lasers, could theoretically reach 20% of light speed, making the journey to Proxima Centauri in approximately 20 years. While still in its conceptual phase, this ambitious project represents humanity's first serious attempt to design an interstellar mission to our closest stellar neighbor. As we continue to study Proxima Centauri and its planetary companion, we're not merely investigating a distant world. We're examining a potential mirror reflecting the diversity of planetary systems throughout our galaxy. The lessons learned from this nearby system will inform our search for life beyond Earth and shape our understanding of planetary evolution in the most common stellar environments in the universe. The discovery of Proxima Centauri B has transformed our nearest stellar neighbor from a mere point of light into a destination, a world we can study, imagine, and perhaps one day visit. It serves as a powerful reminder that even in our immediate cosmic neighborhood, the universe continues to surprise us with its richness and complexity. As we develop increasingly sophisticated instruments to study this enigmatic world, we edge closer to answering one of humanity's oldest questions. Are we alone in the cosmos? This tiny red star, barely visible through modest telescopes, has become a beacon guiding our interstellar aspirations, a testament to how the smallest cosmic neighbors can illuminate the grandest questions of our existence. As we peer toward Proxima Centauri, we're not just looking at a distant star, but potentially toward humanity's interstellar future.